Okay, so today we are going to solve some problems. So I write the problem. So the first problem, suppose G be a group of order 7. Okay, so let G be a group of order 7. Maybe I can write short, I can write suppose the cardinality of a group is 7. Okay, and we have a function. So and pi is a function from G to G defined by pi of x equal to x power 4 for all x in G. Then what can you say about this function pi? Then pi is, so first option 1 1, that is first option is not 1 1, not 1 to 1. Second option is not on to. Third option not a homomorphism, not a homomorphism. And then the fourth option is 1 1 on to and to homomorphism. 1 to 1 on to and homomorphism. Now, what is the information given? G be a group of order 7. So 7 is a prime number. We know that any group of order prime is a cyclic group, and every cyclic group is a abelian group. Therefore, we know that G is abelian. From this information, what we know? G is abelian group. Okay. Now, look at this function phi. So first you have to check this is a homomorphism or not. So therefore, what you have to check pi of xy equal to pi of x into pi of y or not. So by the definition, pi of xy is nothing but xy power 4. But we can, that is xy power 4 is nothing but you have to multiply xy 4 times. Since the group is abelian group, we can interchange this x and y, therefore we get x square. Again, you can interchange this y and x everything, so we can get x power 4 y power 4 because of G is abelian. Otherwise you are not allowed to interchange the elements. So the what is x power 4 is nothing but pi of x, and y power 4 is nothing but pi of y. Therefore pi of xy equal to pi of x into pi of y. Therefore phi is homomorphism. Therefore we can eliminate the third option because this is a homomorphism. Now we have to check if a function is a 1 1 or not. So since phi is a function from a group G to G, and we know that G is a finite set because G contains 7 elements, therefore G is a finite set and domain and codomains are equal. Therefore if you prove the function is 1 1, it is automatically onto, or if you prove the function is onto, it is automatically 1 1. So the domain and the codomains are same set and it is finite set. If it is 1 1, it is automatically onto, or it is onto, it is automatically 1 1. So provided should be finite set and then cardinality should be same. Need not be same set, maybe in anything. So in general, suppose f is a function from some set A to B at the condition that the cardinality of A equal to cardinality of B, then if f is 1 1, then implies f is onto, or f is onto, then automatically f is 1 1. Okay, provided both have same cardinality and finite set. Now to prove, we have to check the function is 1 1 or not. So already we know that this is a homomorphism. To prove a function is 1 1, we have to check the kernel. The kernel of the homomorphism contains only identity element, and the function is 1 1. Suppose the kernel contains more than one elements, the function is not 1 1. Now we have to find that what is the kernel. So what is the kernel of the function pi? By the definition, set of all elements in G which maps to identity element. that is pi of x equal to identity. Now, what are the elements matched to identity? So by the definition again, so that is set of all x in G. What is pi of x? We define x power 4. So x power 4 equal to identity. So x power something equal to identity. Therefore, this 4 may be the order of the element. But we don't know this is the smallest element. Therefore, order of x divides 4. So we know what is the meaning of order of the element. So n is the least positive in this that x power n equal to e, then n is the order of the element. But if x power n equal to identity, we cannot say n is the identity, n is the order. But the order of x divides the number n. Now, we don't know this 4 is the smallest positive integer such that x power 4 equal to identity. But we can say order of x divides 4. Now, for what are the possible values of this order of x? Maybe 1 or 2 or 4. Okay, but we know the theorem, that is Lagrange theorem. If you take any element A in the group G, in the finite group G, then the order of A is always a divisor of order of G. That is always true in a finite group. Therefore, suppose if order of x equal to 2, suppose if you take the order of x equal to 2, then this number should divide the group order, but the group order is 7. 7 is a prime number. Therefore, this is not divides. Therefore, 2 is not possible. Suppose order of x equal to 4, again this should divide the group order. Again, 7 is a prime number, therefore it has only divisors are 1 and 7. Therefore, 4 does not divide 7. Therefore, order of x equal to 4 is also not possible. Therefore, the only possible is order of x equal to 1. So, an element whose order is 1, that element should be identity element. Okay. So, therefore, this should be contains only the identity element. Since the kernel contains only the identity element, therefore the function is 1, 1. Since f is pi is 1 to 1. Since pi is 1 to 1 and the domain and codomains are finite set and the same cardinality implies pi is on 2. Therefore, pi is 1 to 1, on 2 and homomorphism. Therefore, the correct answer is 4 to 1. All others are false. Okay. Okay. Now we solve one more other problem. Okay, from linear algebra we solve some problems. Okay, second problem. Suppose we have a 3x3 matrix. So A be a 3x3 matrix whose eigenvalues are 1, -1 and then 3. It is given. Now, which of the following is true? First option, a square plus a is non-singular. So non-singular means what? It's an invertible matrix. Is non-singular. The second option, a square minus a is non-singular. So we have to find the eigenvalues of a square plus a square minus a, and take the product. If it is 0, it is singular. If it is non-zero, it is non-singular. Okay. So the third option is a square plus 3a is non-singular. And then the fourth option is a square minus 3a is non-singular. So which are the following is true? Now we have to find the eigenvalues of each of the option. Now we know the eigenvalues of a. So what is the eigenvalues of a? Eigenvalues of a are 1 minus 1 is 3. Now what is the eigenvalues of a square? Just to square each eigenvalue. Therefore 1 square is 1, minus 1 square is 1, 3 square is 9. So 119 are the eigenvalues of a square. Now look at the first option. What is the eigenvalues of a square plus a? Just sum it. The eigenvalues of a square plus a is 1 plus 1 is 2, 1 minus 1 is 0, and then 9 plus 3 is 12. Now determinant is nothing but product of the eigenvalues. We get a 0 because 0 is the one of the eigenvalues. Therefore, determinant of a square plus a is 0. Therefore, it's a singular matrix. Therefore, the first option is false. Now, find the eigenvalues of a square minus a. So, this is eigenvalues of a. What is the eigenvalues of minus a? Just you have to multiply minus to reach them. Therefore, minus 1 plus 1 minus 3. Now, sum these two. So, what is the eigenvalues of a square minus a? That's nothing but 1 minus 1 is 0, 1 plus 1 is 2, and then this is 6. Anyway, again 0 is the one of the eigenvalue, therefore determinant is 0. Therefore is singular matrix, but not singular. Therefore second option is false. Now again 3 times a. What is the eigenvalues of 3a? Just multiply 3 to the each one. Therefore 3 minus 3 comma 9. These are the eigenvalues. Now sum these two. What is the eigenvalues of a square plus 3a? A square plus 3a is 1 plus 4, 3 is 4, minus 3 plus 1 is minus 2, and then 9 plus 9 is 18. Now all the eigenvalues are non-zero, therefore determinant is non-zero, therefore a square plus 3a is invertible, therefore it's not singular. But if we take minus 3a, so what is the eigenvalues of minus 3a? So that is, you have to multiply minus, therefore minus 3 plus 3 minus 9. Now add the eigenvalues of a square and a square and 3a. What you'll get? So I think, am I correct? Yeah. So therefore here we have a plus 9, minus 9 and then plus 9. Okay. Therefore sum is 0. Therefore determinant 0 is singular matrix. Therefore last one is false. Okay. So any doubt in this? Okay. Now we solve the next problem. Third problem. Again from linear algebra. Suppose we have a linear transformation T from R3 to R3. Okay, R3 to R3 be a linear transformation. Okay, and I is the identity transformation. Okay. Now, suppose if there is a non-zero number or there is a scalar C and a vector and a non-zero vector and non-zero vector x, but x in R3, the scalar in R, such that it satisfies the condition such that t times x equal to c times x. Okay, that means what? C is the eigenvalue, the corresponding eigenvector is x. Okay, then the question is, what is the rank of t minus c times identity? Okay, the options are cannot be 0, cannot be 0, cannot be 1, cannot be 2, cannot be 2, and then the last option is cannot be 3. So what do you mean by rank actually? Rank is nothing but dimension of the range space. Okay, since look at this one. So again you have to apply rank and nullity theorem anyway. So since clearly if you consider this transformation t minus c times I, this is a function from R3 to R3 again. Okay, it's because I is identity map, is a map from R3 to R3. If you multiply some scalar, this is also a function from R3 to R3. Now this is also a linear transformation. Okay, now apply rank nullity theorem. So what do you get? Rank of t minus c times I plus nullity of t minus ci equal to dimension of the domain. What is the dimension of domain? Is 3. Okay. Now we have to find the value of this rank of T minus Ci, and therefore we have to check what is this number, and that means what is the null space. So nullity is nothing but dimension of the null space, that is n of t. So first we have to check what is n of t minus Ci. It contains any non-zero element or not. Since it is given that Tx equal to C times x, where x is a non-zero, this is given, okay, there is some non-zero vector x such that Tx equal to Cx. Therefore you can take everything one side and then take x outside. Therefore T minus C times I into x equal to 0. So what is the definition of n of t comma Ci? Is set of all vector v such that T minus C times identity at a vector v takes 0. Now clearly this element x is a member of null space, and this should be non-zero number. Therefore dimension should be at least 1. We don't know the exact dimension, but dimension cannot be 0. So when a subspace dimension 0, only when it contains 0 element only, but the null space contains one non-zero element, namely x. Therefore the dimension of null space of T minus Ci. So this is nothing but nullity. Nullity of the operator T minus Ci is at least 1. We don't know this is exactly 1, but at least 1, cannot be 0. Therefore, by rank nullity theorem, we call this equation number 1. This number is at least 1. Therefore, this number cannot be equal to 3. If it is 3 means this should be 0, because the sum is 3. This number is bigger than 1, therefore this should be less than or equal to 2. Therefore, it cannot be 3. So that is answer. So maybe it's 2, maybe 1, maybe 0 sometimes. If it takes 0 function, then it is 0. Therefore, it cannot be 3. So this is the correct answer. Got it? Because you have to apply rank nullity theorem for this operator T minus Ci, and then the null space contains at least one non-zero vector. Therefore, dimension is at least 1. Therefore, rank is at the most 2. Rank is at the most 2, cannot be 3. Okay. Any doubt in this?
No, sir.
Yes, no doubt. Okay. Now, next problem. From group theory, fourth problem. Suppose we take the group G is contains the element 1, 2, 3 up to 16. So this is a group with respect to multiplication modulo 17. This is a group under multiplication modulo 17. 17 is a prime number. If you take all the, so actually it's nothing but Z p star, Z17 star. That is, you have to remove 0 from Z17. That is our G. Okay. That is Z17 star is nothing but G. Now the group G is a group with respect to multiplication modulo 17. Question is, what is the multiplicative inverse of 3? So okay, so sorry, they are asking what is the order of, not the inverse, the order of the element 3. What is the order of an element? Order of an element 3. So for that means what? 3 power something should be 1 modulo 17. Okay, so what is the number? So the options are, first option 4, second option is 6, sorry 8, third option is 12, and then fourth option is 16. Then what is the answer? Now actually, so what is that? That is 3 power something should be identity. So what is that? So 16. Since we know that in number theory you study the Wilson's theorem, sorry, Euler Fermat's theorem. So what is the Fermat's theorem says? A power p minus 1 is congruent to 1 modulo P. Okay, this is a Fermat's theorem. Okay, now here P equal to 17 because 17 is a group order, it's a prime also. Therefore, here A equal to 3 and then P equal to 17. Therefore, we get 3 power 16 is congruent to 1 modulo 17. Therefore, 16 is the order of 3. Simply you can say. Okay. So we have to use the Fermat's theorem. So otherwise Euler's theorem. So Euler's Fermat's theorem is nothing but particular case of Euler's theorem. So Euler's theorem is for general case. So what is the Euler's theorem says? Suppose the GCD of A comma n equal to 1 implies that A power pi of n, Euler phi function pi of n is congruent to 1 modulo n. So this is the Euler's theorem. If we take n equal to prime number, pi of p is nothing but p minus 1. So this is the Fermat's theorem. Fermat's theorem. Okay, using Fermat's theorem, we can say the order of 3 is 16. Okay. Now, the next problem. So, any doubts so far? Okay. The next problem. So, I already said that what is the dimension of skew symmetric matrix. Maybe I read the problem. I think fifth problem. So the fifth problem says the number of unknowns are the maximum number of different possible non-zero entries in a skew symmetric matrix. Of order n by n matrix. So the options are, first option 1 by 2 into 1 by 2 times n square minus n. So actually it's nothing but dimension. They are asking the dimension of the skew symmetric matrix of order n. And already, so 1 by 2 times n square plus n is the second option. Third option is n square. The fourth option is none of the above. None of the above.
Answer is A, sir.
Yeah, because n into n minus 1 by 2. Yeah, so this is the correct answer. Okay. Now, one more problem from linear algebra, sixth problem. Suppose V is a vector space. Vs means vector space. And this L of S means the subspace spanned by S. That means all possible linear combination of elements of the S. S is a subset of V. Okay. So this L of S is nothing but all. I hope everyone understands this. So it's nothing but A1 x1 plus A2 x2 plus etc. some an xn such that these xi's are varies in S and this A is our scalar. Suppose I take F is that field. Okay, here n is anything. Okay, all possible linear combination of elements of S is nothing but L of S. Sometimes we call this spanning set, span of S. Okay, this is a notation. Now, which of the following is true? Okay, then which of the following statements is true. Okay, statement is incorrect. Sorry, statements is incorrect. So the first option, L of S is a subspace. This is a subspace of V, vector space V. And second, if suppose A is a subset of B, implies that this L of A is a subspace of L of B. And then the third option, if S is a subspace, then L of S equal to S. Subspace of B if and only if L of S equal to S. And then the last option, if A not equal to B, implies L of A not equal to L of B. Okay. Now the L of S, S is any set in the vector space. The L of S is always a subspace. Why? Since this A's are varies over the field F, right? If you take all the A's are 0, we get 0 is a number of L of S. Therefore, identity element is there. Again, if you add two linear combination, we'll get the new linear combination, again members of elements of S. Therefore, sum is also there. If you take scalar multiplication, if you take some alpha is some scalar, and if you take any element here, if you multiply alpha, then what you'll get? Alpha times a1 x1, alpha times a2 x2, and so on. So again, this is a member of sum. Therefore, clearly the spanning set is always a subspace. So that is not incorrect. It's a correct statement. Okay. Now look at this one, second one. If A is a subset of B, then L of A is a subset of L of B. It's a subspace also because every element of A is an element of B. We know this one. So we have to prove that L of A is a subspace of L of B. It is enough to prove that L of A is a subset of L of B. Because already we know that L of anything is a subspace. Okay. So it is enough to prove that this L of A is a subset of L of B. Since it's a subset of this one, and the L of A is itself is a subspace, therefore this is a subset of L of B, therefore it's a subspace of L of B. And what we know, A is a subset of B is given. Every element of A is a member of B. Now we have to prove that L of A is a subset of L of B. Therefore we start some arbitrary element. Suppose I take some B belongs to L of B. Therefore B is of the form some scalar alpha times x1 plus etc. some alpha times some xn, where this alpha i's are scalars and this xi's are varies in capital A. And since these xi's are in A is a subset of B, therefore these xi's are in B. Therefore this belongs to L of B. Because this alpha 1 to alpha is a scalar, this x1, x2, xn's are in B. Therefore this B belongs to L of B. Therefore L of A is a subset of L of B. Since L of B is a subspace, therefore this subspace. So this is also a true statement. This is also a true statement. Again, if you take the third statement, if S is a subspace of B, then L of is always equal to L of S equal to S. And if L of S equal to S, S is a subspace. This is a theorem actually. We can easily prove. This is also a correct statement. Now look at the last option. Suppose if you have two different sets, that is A not equal to B, need not be L of A not equal to L of B. Sometimes L of A equal to L of B. Why? So for example, if you take in the real case, suppose I am taking R2. Okay, in R2, I am taking A equal to the standard basis. Okay, better take the standard basis 0, 1, 1, 0. Okay, this is one set. I am taking another set B is again take 1, 0, 0, 1, and taking some other element. Suppose I am taking 0, 2. Now definitely A and B are not equal. Because A contains 2 elements, B contains 3 elements. Therefore definitely A not equal to B. Therefore these two sets A and B satisfy our assumption A not equal to B. Now what is L of A? So actually we know that this form a basis. Therefore L of A is nothing but the whole set R2 because it's basis. Even if you take what is L of B, again this is equal to R2 because the last element is nothing but the scalar multiple of the second element. If you multiply 2, you will get this one. Therefore, only these two element is enough to span the entire space R2. This is extra one more element. Actually, this element uh, does not spoil any our definition because this is scalar multiple of the second element. Therefore, L of B also R2 because A and B contains the basis element, namely the 1, 0, 0, 1 is the basis. Then the L of A and L of B equal, both are equal. Therefore, these two sets contradicts the last statement. A not equal to B, but we get L of A equal to L of B. Therefore, they are asking incorrect statement. Therefore, these are all correct statement. The last one is the incorrect statement. Okay. Any doubt? Okay. Now we solve the next problem. Okay. Actually, that is directly they asking definition. I think we solved almost all the problems. This is question number 7. So the 7th question says, study the following statement about the square matrix. Which of the following is true? First statement, the sum of the eigenvalues is equal to trace. Okay. Sum of eigenvalues of the matrix A equal to trace. And second statement, product of the eigenvalues is determinant. Product of eigenvalues of A is nothing but determinant of A. Okay. Third statement, all the eigenvalues of A are non-zero if and only if A is non-singular. All eigenvalues of A are non-zero if and only if A is non-singular. The fourth option point, suppose if A inverse exists, if A inverse exists, then the eigenvalues of A inverse are the reciprocal of the eigenvalues of A. The eigenvalues of A inverse are the reciprocal of A, eigenvalues of A. The reciprocal of the eigenvalues of A. Then which of the among the following is correct with respect to the above expression? So clearly everything is true. Okay, which of the statements are true? First one is true because sum of the eigenvalues is nothing but trace of the matrix. Product of the eigenvalues is nothing but determinant of the matrix. All the eigenvalues are non-zero, then the product of the eigenvalues is nothing but determinant. Therefore, determinant is non-zero. Therefore, A inverse is non-singular or invertible or sometimes called a non-singular. If you know the eigenvalues of, so A inverse exists means what? That means determinant is non-zero. So A inverse exists means what? All the eigenvalues of A are non-zero. Therefore, we can define the reciprocal. This is the eigenvalues of A. This is also true. Therefore, all the statements are true statement. Okay. Now maybe some other next problem. Okay, these are all. So I say, otherwise, you have any problem sheet, you just send to me. We will discuss it. Okay. So you again from starting, look at the problem if I miss anything. So far, any doubt? So almost we solve all the problems from this previous year questions. Okay. And anyway, I skip some of the problem. That is a very simple one. So for example, if I write that problem, which of the following is a subspace? We can easily check that this is subspace or not. Okay. So maybe we write the problem. So this is which of the following is subspace? Which of the following is which of the following is a subspace of R3? So first set, first option. So set of all x comma y comma z in R3 such that x plus 2y equal to 0 and then 2x plus 3z equal to 0. And then the second set of all x comma y comma z in R3 such that 2x plus 3y plus 4z minus 3 equal to 0 and then z equal to 0. And then the third one is set of all x comma y comma z in R3 such that what is the condition? X should be positive or 0 and y also greater than or equal to 0. And then the last option, set of all x comma y comma z in R3 such that x minus 1 equal to 0 and y should be equal to 0. Now clearly, so subspace means what? It contains the 0 element, 0, 0, 0. Now look at the second set, 0, 0, 0 not satisfy the condition. Because if substitute 0, 0 here, this term is 0, but this term is non-zero. Therefore, we get minus 3 equal to 0. That is not possible. Okay. Therefore, what is the correct answer? A is the subspace. Because look at the third option. If we take the negative numbers, if you multiply a vector to a negative number, the scalar multiplication is not there. The last option again 0, 0, 0 not satisfy this condition. Therefore, the subspace are only the subspace is first option. Okay. Now, one more interesting problem. We have to find the dimension of the subspace. So this type of problem they will ask regularly. So that is what is the problem. Suppose consider the subspace W is from R10, that is this contains 10 tuple x1 comma x2 comma etc x10. So this is element in R10 such that what is the condition? The any xn equal to xn minus 1 plus xn minus 2 for what values of n? For 3 less than or equal to n less than or equal to 10. Okay. If n lies between 3 and 10, this xn can be replaced as xn minus 1 plus xn minus, that is sum of the previous two terms. Now what is the question? What is the dimension of W? So dimension of W equal to, so the first option, so first option is 2, second option is 3, third option is 9, and the fourth option is 10. So what is the, so that we have 10 unknowns, x1, x2, etc., x10. Okay. Using this condition, we have to reduce the unknowns. Now, this condition is holds only for n values taken from 3 to 10. Suppose if we take x3, so x3 is nothing but sum of previous two term, that is x1 plus x2. Okay, therefore now I am writing x1 comma x2 comma x3, but instead of x3 I am going to write x1 plus x2. Okay, now what about x4? x4 is nothing but sum of the previous two term, that is x2 plus x3, but we know that x3 is nothing but x1 plus x2. So therefore this term 2 times x2 plus x1. Anyway, the unknowns we are using x1 x2, and if we take x5, so this is nothing but sum of the previous two term, that is x4 plus x3, and we know that x4 is also yes, in terms of x1 x2, x3 also in terms of x1 x2. Therefore if you take anything up to the last term, only two unknowns we are using, namely x1 and x2. Therefore the number of unknowns is 2, therefore dimension is 2. Okay, so any doubt in this? So we have to reduce the unknowns, number of unknowns. Okay, so any doubt you can ask now. Okay, now another question from group theory, 10th question. Suppose G is a cyclic group of order 24. G be a cyclic group of order 24. Now the question is the total number of isomorphism. Total number of group isomorphisms of G onto G onto itself. So how many isomorphisms are there from G to G? And G is a cyclic group. I already said that isomorphism from domain and codomains are same set, we call it an automorphism. Okay? And in a so number of automorphism in a finite cyclic group of order n is nothing but, what is that answer? Pi of n. So here pi of 24. So the options are, first option is 7, second option is 8, third option is 17, and then the last option is 24. So they're asking the number of isomorphism from G on to G is nothing but automorphism. And we know the result, the number of automorphism. So we quickly recall the result. The number of automorphisms of a finite group, of a cyclic group of order n. Cyclic group of order n is phi of n, Euler phi function. So therefore in this case n equal to 24. First you have to write 24 is a product of prime powers. So this is nothing but 12 into 2, and this 2 cube into 3. Sorry, 2 cube into 3 plus 8 into 3 is 24. Right? Therefore, what is pi of 24? By the formula, 24 times the prime numbers are 2 and 3. Therefore, 1 minus 1 by 2 to 1 minus 1 by 3. Now, if we simplify this, 24 into 1 minus 1 by 2 is 1 by 2. 1 minus 1 by 3 is 2 by 3. Now we can cancel 1 3 and then we 2. We get this is 4 times 2, therefore 8. So there are 8 isomorphism we can define from G to G. So the answer is 8. So this formula is very important. This formula only for cyclic group of order n. Suppose it is given that infinite cyclic group, we have only 2 automorphism. Take finite cyclic group of order n, it has a pi of n automorphism. So, but anyway, they didn't ask. They mentioned automorphism, but they say that it's isomorphism from G onto itself. Therefore, should be automorphism. Okay, the one more important thing. Okay. Now, another problem from group theory. Which of the following condition implies that G is abelian? 11th question. Which of the following condition implies that G is abelian? Which of the following conditions on a group G implies that G is abelian? So G is given for what condition of G that G become abelian group? Okay, that is the question. So the first one, the group of order prime square. So the first one is the order of the group, the order of G is P cube, prime cube, for some P, for some prime P. So from this condition, can we say is abelian? No, because we know that group of order prime square is abelian, but the prime cube may not be abelian. Okay, no. Look at the second one. Every proper subgroup is cyclic. Every proper subgroup of the group G is cyclic. From this, can we say G is abelian? Now, third option, every proper subgroup is normal. From this, can we say G is abelian? So every proper subgroup is normal subgroup. Then can we say normal in G? Every subgroup of G is normal in G. Then can we say G is abelian? Then the last one is, if the function f from G to G defined by f of x goes to x power minus 1 for all x in G, if suppose this is a homomorphism, can we say G is abelian? Yeah. So clearly the first one is false, because group of order P is abelian, group of order P square is abelian, but group of order prime cube need not be abelian. Therefore, first option is false. Now look at the second option. Therefore, first one is false. Every proper subgroup of G is cyclic, then can we say the group is abelian? Okay. Okay, I will come to that. Anyway, we take the same example. So what is the example I am taking? Quaternion group. So you take Q8. So Q8 is nothing but plus or minus 1, plus or minus I, plus or minus J, then plus or minus K. Okay, it contains 8 elements. Okay, here the identity element is 1. So the subgroups are either contains plus or minus 1 and plus or minus I. This is one subgroup. And then either plus or minus 1 and then plus or minus J is another subgroup, or plus or minus 1 plus or minus K are the another subgroup. So these are the only subgroups, proper subgroups. Or if we take the trivial, therefore I list the subgroups. Minus 1 plus 1, this is one subgroup, proper subgroup. And then plus or minus 1 plus or minus I, this is another subgroup. Again plus or minus 1 plus or minus J is another proper subgroup, plus or minus 1 plus or minus K. So what is the conditions? I square is minus 1, J square is minus 1, K square is minus 1. And then I into J is K, J into K is I, K into I is J. We know that one. Okay. Now, this is a cyclic group. Because order is 2, therefore any group of order prime is cyclic, therefore this is cyclic. Now, this contains 4 elements. This is generated by I or minus I. Therefore, this is also a cyclic subgroup. And this subgroup is generated by J or minus J. This is also a cyclic subgroup. And this subgroup is nothing but generated by K. K square, K cube, K power 4. K power 4 is 1. So, this subgroup spanned by single element K or minus K. Okay, therefore, every proper subgroup is cyclic group, but the group is not cyclic. This quaternion group is actually non-abelian group. So this is a non-abelian group. So every non-abelian group is non-cyclic. If it is cyclic, and we know that every cyclic group is abelian group, therefore this group become a abelian group. But we know that this is a non-abelian group. Why this is a non-abelian group? I into j not equal to j into I. Why? Because I into j value is k, but j into I value is minus k. Therefore, k not equal to minus k. Therefore, this group is non-abelian group. Therefore, implies non-cyclic group. Non-cyclic. But every subgroup is cyclic. So, it satisfies the second property, that is every proper subgroup is cyclic. From this, we cannot say G is abelian. Okay, therefore, the second option also false. Now, look at the third one. Every proper subgroup is normal. Then it is, from this can we say the group is abelian. Now, except the first subgroup, look at the other subgroup. Everything order 4. So, order of this subgroup is 4, order of this subgroup is 4, order of this subgroup is 4. And the order of the group is 8. And we know that if G by H, the number of elements in the G by H is 2, from this we can say H is normal. H is a normal subgroup. If the index is 2, then H is normal. So therefore, definitely index of these 3 subgroups are 2. Because 8 by 4, 8 by 4, 8 by 4, everything is 2. Therefore, from this theorem, we can say these subgroups are normal subgroup. This is normal, this subgroup is normal, this subgroup is normal. Only thing we have to check that this is normal or not. Okay, so clearly this is a normal. You can easily check that. Okay, so therefore every proper subgroup is normal, but the group is not abelian. Therefore, from this condition, we cannot say G is abelian. This quaternion group is very important group because this group is example for the second option as well as third option. We eliminate the second option, third option using this one single group. Okay, the group is non-abelian, but every subgroup is normal. Okay, but theorem say if you take a suppose a group is abelian group. In the abelian group, if you take any subgroup, that is normal, but the converse need not be true. That is, all the subgroup are normal subgroup, but the group need not be abelian. That is a example. This Q8 is an example for that one. Now look at the last option. F is a function from G to G defined by f of x equal to x inverse. Given that, so the last option, it is given that f of x equal to x inverse. It is given that it's a homomorphism. Therefore, it satisfies the condition that f of xy equal to f of x into f of y. Okay, now implies that what is f of xy by the definition xy whole inverse. This is equal to what is f of x? X inverse. And this f of y is nothing but y inverse. But in group theory, this result is true. So already said that f of AB whole inverse is nothing but the reverse, B inverse into A inverse. Okay. Therefore, the right hand side, if you can say this equation, xy whole inverse is nothing but y inverse x inverse equal to x inverse y inverse. Okay, so what we have to prove? We have to prove that abelian, that is, we have to prove xy equal to yx for all x. Okay, so anyway, we can adjust. First, you have to cancel this x inverse. So multiply x inverse x both side. Therefore, the left hand side we have y inverse, right hand side we have x inverse, y inverse x, because we multiply x, this x inverse x cancel. Now I'm going to multiply x to the right hand side. Therefore, we can have a x here and this x inverse cancel. If you multiply y the right hand side, we get this is cancel. If you multiply y first, this is cancelled. Therefore, we get yx equal to xy. So finally, anyway, we get xy equal to yx for all xy. Therefore, if f of x equal to x inverse is a homomorphism, if and only if G is a abelian group. This is very important here. If G is abelian, then this function is a homomorphism. If G is not abelian, this x goes to x inverse is not a homomorphism. Okay. If x equal to x inverse is homomorphism only when the group is abelian group. Therefore, from this condition, we can say we get a G's abelian group. Okay, it's a very important function. Okay, and then we solve other problems. Almost we solve the problems. So if you have any problem, you just send to me. We will discuss if you have any free time. So almost we solve the problems from group theory and then linear algebra. If just you try some other problems, if you not get, we will discuss it. Just to try the GATE exam question papers or any other entrance exam question papers, just to try to solve the problems from linear algebra and then group theory. If you not get, just to inform me, we will discuss it. Okay, so any doubt? Anyway, I can stop now.